are you trying to figure out once you have the diagnostics run, like the different materials that you should be using inside that chamber? Is that the ultimate goal?
So the way
Kind Go
the
ahead.
experimental study is loosely designed right now is we're trying to isolate variables. Um, so whether that's with doing actual primer events or whether that's creating primer type events with simulated temperatures, simulated gas velocities, or simulated solids ratios, those variables we are going to try to control in very laboratory type experiments. Yes, there could be changes that come later, innovations that come later, but what we're trying to do is apply the control and the results to existing formulations or existing geometries. Those are the main two contributors to propellant burn right now is geometry and chemistry, and to some degree the confinement of the system, but we're going to be controlling that as well. But the innovation later would be changing those two variables is what chemistry can we change? Maybe it's coatings to enhance the heat transfer. Maybe it's geometry to enhance the surface area so that it ignites differently.
If I can add one more thing to that, is to
Mm-hmm.
say that the one distinction between John and I is that in my environment, everything's very much on a small scale. Our whole system probably won't be much bigger than like an ice cream cone. I'm trying to think of a cylindrical cone kind of, whereas
Yeah.
the application is much bigger than that. So what we learn on the small scale usually will translate. I mean, we know how to make it translate to a larger scale, which would be the application. And then John's company can seamlessly, transition that information to the field and the application. And hopefully by then, some of the students will be employed also too. So it's a nice segue for students to, get some field experience before they graduate.
Yeah,
Definitely.
I'll reiterate that is the goal is that this diagnostic and the expertise from trained students keep growing with the application complexity.
So how do you expect that these solutions that you're developing will meet the cutting edge standards of engineering and then the strict requirements of defense applications? Like if you could have a crystal ball and look forward to that, because I mean it is at the early stages, but just tell me your expectations on it.
Some of the requirements that I think we're targeting that are of interest to us and to the Army or the Department of Defense are safety of the system, the gun systems, and safety can be related to all kinds of initial conditions that are applied, whether it's environmental, whether it's mechanical damage to the system, whatever. So by understanding these early events, we hope that we can make that safety margin bigger and keep our soldiers safe. But then the ultimate goal is to enhance the performance. So gun systems obviously, or not obviously, but we are already shooting them at maximum performance. That's what our engineers and weapon designers have pushed right now. But with better understanding, they can optimize this little piece or that little piece and keep marching that performance level up. Performance can be characterized a couple different ways for guns, whether it's increased velocity, increased range, increased accuracy, all those kind of things can be metered later. But like she said, in the small scale experiment, you're just getting understanding. As it grows to experiments at element in maybe a couple of years, where now it's a full scale gun that we're testing with the same diagnostic, I think then you'd get closer and closer to demonstrating the metrics that you're discussing that the Army wants.
Okay.
And to add to that, I mean, the flow physics are not trivial, right? I mean, when you have a gas and a liquid and a solid and high temperatures and in a confined environment where the pressure is growing and everything's highly transient, Like the environment is extreme. And because of that, it's complicated. The physics are complicated. And so nobody really has great models to describe that. And a lot of our advances are based on trial and error. Even, I mean, that's the reality, even today. And so now that we have the technology to kind of inform those physics, let's use it. Let's step back and try and deconvolute this very complicated puzzle. And like John said, constrain the variables. Just look at this. Just look at flow velocity. Just look at gas temperature and how those interact with a particle bed. Just look at this. And then you just keep adding complexities to that to understand how the whole energy balance unfolds during a reaction and those flow conditions. So, I mean, we have this great opportunity now to scientifically make advances and not just make advances based on intuition, experience, and trial and error.
Right, which actually is a perfect segue to my next question, because I'm curious, what role do emerging technologies such as AI, robotics, and material science play in the development of these solutions?
One thing that has grown a lot since my early days at the combustion lab is the high-speed camera. So like the capability of the high-speed cameras has grown a lot, and that's a lot based on electronics as well as memory, like write speeds to memory, all that kind of stuff. So this is allowing us to get almost 1,000 times more data than we could have gotten 20 years ago. Faster time scales and more pixel resolution. Those are both huge to this particular diagnostic, but more than that, like all of Pantoya's students are, they have to be fluent in various softwares. So they're almost writing their own software to do this temperature analysis. And that has a lot of capability and nuances to it on how it's calibrated and how it is running its code. So that's one big part of it, I'm going to say, is the software and electronics. But then, like I said, in the future, I expect that there's other partners that may come into this relationship, like Picatinny, where they are providing us new samples that are made in new ways, and there's a lot of subject matter experts up there, chemists and materialurgists and things like that, that have hunches of what would be improved, but this diagnostic would be able to prove or disprove that faster.
Do you guys use digital twins or any augmented reality or virtual reality for any of that? No?
No, good communication is really important. So whenever I have a collaborator, I always try to make sure that the student connects with that person at least monthly, if not more than that. Emails are good. Conversations on the phone, quick conversations, those are good. Like, okay, maybe a Zoom meeting once a month or once every 2 months. But I think it's important for the students to know that they have to maintain the communication in order for everybody to move forward in a really, healthy and positive way.
Can you tell me about the sensors that might be used in the vision system, or can you tell me about the vision system, the cameras? What is there? Does it use LiDAR?
Sure.
What's used?
And if I can just step back, just because you did ask about AI and machine learning. And all of that machine learning, artificial intelligence requires large data sets, right? And sort of historical data to start informing predictions and so forth. And so that's what we're doing right now. We're generating the data that could be used by people who can apply artificial intelligence and machine learning to formulate like the propellants of the future. So we're not actually doing AI or machine learning, but right now, those kind of models are being generated from the models that we're trying to make accurate. And then we'll be able to provide them with lots of data that's absolutely essential for that road. So that's exciting. And the question that you just had was about
About the sensors and about
Oh, the
the
sensor.
vision
Yeah,
system and like what's being used to,
right. You know, I'll tell you, it goes back, oh gosh, to the 1700s when a gentleman named Max Planck realized that radiation follows this law that we'll call the T to the fourth law. And he said that that condensed phases emit, as we can assume, as black bodies or gray bodies. We'll call them gray bodies are not perfect. Black bodies are like an ideal emitter and absorber of radiation. It's the term we use. Whereas gray bodies kind of notch it down, but it assumes that the emissivity of a body is fairly constant. So under those fundamental laws, we can apply them to the measurements of emission, light intensity emission, in a discrete wavelength. And we can take multiple measurements in multiple wavelengths. And from those multiple measurements, we can use Planck's law and do something we'll call ratio pyrometry, and basically use that equation for two different emission intensities that are associated with a given wavelength. And you get this function of temperature. And from that, those measurements, that's kind of how you back calculate temperature. So the sensors work to discretize light into a single wavelength and quantify its intensity. And it works because we can take multiple measurements over multiple wavelengths to get multiple intensities. So we don't have to know details about the emissivity of the body. We just assume that the emissivity doesn't change all that much. And at these temperatures, pretty much everything's behaving like an ideal emitter and absorber of energy. So everything's behaving like a black body. And if we make those assumptions, we get these relative indications of how thermal energy moves through a system. With the resolution we have, we can get down to about, the sensors allow us to get down to about 2 or 3 microns. Like a little pixel that's about 2 microns by 2 microns. And we can get down to, maybe 200,000 frames per second. So we're getting quality temporal and spatial data that will allow, those sensors will allow us to understand the movement of heat.
does the environment around change the results?
You know, yes and no, because the sensors, the way this works is we pretty much are monitoring condensed phases. So it doesn't really matter if the gases are at 5 degrees or 1,000 degrees. Gases don't emit as well as condensed phase species. So the sensors are detecting the liquid droplets that are burning in an aerosol. They're detecting the solid parts, the char. They're detecting anything that's in the condensed phase, liquids or solids. So the environment, while that environment might influence those condensed phase measurements, we're not really detecting the environment. But because of an energy balance, we can infer what the environment is like because we know how much energy is going into the system. It's all the chemical energy from the reactants. So we can tweeze out what's coming out in the gas phase versus the condensed phase, what's coming out as conduction and convection versus what's coming out as radiation.